Now, in this video, we are going to see about the applications from Ellingham diagram. Very important question. So, applications from Ellingham diagram. So, what is the use of Ellingham diagram? Using Ellingham diagram, we can select what type of reducing agent like carbon, carbon monoxide, hydrogen or any other metals. So, which type of reducing agent we are going to use for the reduction of metal oxide to metal, and also at what temperature we are maintaining for their decomposition. So this is the use of Ellingham diagram. From that diagram we came to a point. 4 points are there. The first point, using Ellingham diagram for the formation of silver oxide and mercuric oxide is at the upper part of the diagram. When we seeing the graph, their decomposition temperature is 600 and 700 respectively. When we are seeing the graph, I will show. See, for the formation of silver oxide and mercuric oxide, that means we know reduction process means the silver oxide Ag2O decomposed to give silver and oxygen, and mercuric oxide decomposed to give Hg and O2. At what temperature means at 600 Kelvin, and mercuric oxide changes into mercury at 700 Kelvin. That means at these moderate temperature only they are unstable. That means below these temperatures they are stable one, they are not decomposing, but at moderate temperatures like 600 and 700 Kelvin they decomposes into metals. So, and will decompose on heating even in the absence of reducing agent. So, for the decomposition of silver oxide to silver and mercuric oxide to mercury, there is no need of any type of reducing agent. When we heat that oxides at 600 and 700 Kelvin, it automatically reduces to silver as well as mercury. So, here there is no usage of any type of reducing agents. We don't want to use carbon or carbon monoxide. Just at heating these temperatures, silver oxide reduced to silver and mercuric oxide is reduced to mercury. See in the graph, silver combined with oxygen at a silver oxide, and mercury combined with oxygen forms mercuric oxide. At these temperatures only these oxides are stable. When it reaches 600 and 700 Kelvin, it starts to decompose to form metals. Silver oxide as a silver and mercuric oxide to mercury. So, there is no need of usage of any reagents, any reducing agents such as carbon, etc. So, at a moderate temperature, it starts to decompose and it is undergoing reduction process. The second point in the applications from Ellingham diagram. Ellingham diagram is used to predict thermodynamic feasibility of reduction of oxides of one metal by another metal. See here, thermodynamic feasibility means whether the reaction is possible, whether it requires more temperature or less temperature for the full completion reduction process. So, when one metal, any metal oxide, that is MO is a metal oxide, adding reducing agent, changes into metal oxide, changes into metal, that is reducing agent, accept the oxygen to form as an oxides. So at what is the temperature we need and what is the delta G naught value. So using this only we are predicting the feasibility of the reaction, del G and T, because it is a thermodynamic feasibility process. So Ellingham diagram is used to predict the thermodynamic feasibility. That means at what temperature and what is the delta G value, whether it is a positive or negative. These can be determined from the Ellingham diagram. See, for the example, for the formation of chromium oxide. So listen carefully. For the formation of chromium oxide lies above that of the aluminium, meaning that aluminium oxide is more stable than chromium oxide. Hence, aluminium can be used as a reducing agent for the reduction of chromic oxide. See in the graph, chromium oxide is above the aluminium oxide line. There are so many lines are there. For the formation of chromium oxide, one line is there. For the formation of aluminium oxide, one more line is there. But the line, if you see the graph, the chromium oxide line is above the aluminium oxide line. This represents that aluminium can reduce the chromium oxide. That means those oxides which are below the lines, aluminium can be using as a reducing agent for the reduction of chromic oxide. However, it cannot be used to reduce the oxides of magnesium and calcium which occupy the lower position than aluminum oxide. So these examples I will explain with the help of diagram. See in the graph, aluminium plus oxygen gives aluminum oxide, the line is here. But above that, manganese oxide formation, chromic oxide formation. So the metals which are below that lines, that means here the zinc, here copper, nickel, iron, zinc, chromium, manganese, they are all formation of oxides corresponding copper oxide, nickel oxide, iron oxide, chromic oxide, manganese oxide. So they are all below the aluminium is below that all these lines. Hence aluminium can be using as a reducing agent for all these metal oxides to metal. That means for the conversion of chromic oxide to chromium, manganese oxide to manganese, zinc oxide to zinc. So we can use the aluminium. But this aluminium cannot be used to reduce calcium oxide. So by seeing the diagram above, when we compare all the oxides, calcium oxide here is fully below that graph. So calcium oxide alone can used to reduce all the oxides, or we can use calcium metal. Yes, calcium metal is using as a reducing agent for the decomposition of aluminum oxide to aluminum, manganese oxide to manganese, chromic oxide to chromium. So these are all the points from the second. See one thing, carefully you listen. So those metals which are lying down in the Ellingham diagram, that metals is acting as a good reducing agent for reduction of all the metal oxides to metal. So here copper oxide is less, here the copper is very less, nickel then compared to iron. So overall when we compare, seeing calcium is a good reducing agent than aluminium, than manganese. So the best reducing agent is for all the metal oxides to metal is calcium. The third point in the application is the carbon line cuts across the lines of many metal oxide. That means if you see the graph, there is a pink line which is crossing towards down. The carbon line cuts across the lines of many metal oxides, and hence it can reduce all those metal oxides at a sufficiently high temperature. That means all the metal oxides can be converted into metal at a maximum high temperature. So the carbon can be used. For example, in the Ellingham diagram, for the formation of FeO and CO, that is formation of FeO means for iron combined with oxygen to form FeO, and CO interacts around 1000 Kelvin. So below this temperature, below 1000 Kelvin, the carbon line lies above the iron line, which indicates that FeO is more stable. That means below 1000 Kelvin, FeO is more stable. When it crosses 1000 Kelvin, and hence at this temperature range, the reduction is not thermodynamically feasible. That means below 1000 Kelvin, the FeO is more stable one. So the reaction does not take place. That is, FeO more stable means it does not decompose to give metal and oxygen. So therefore the reaction is not possible. Reduction is not thermodynamically feasible at 1000 Kelvin. However, but 1000 Kelvin above means the carbon line below the iron line. That means if the 1000 Kelvin means the iron line is above the carbon line, so reduction is not possible. But above 1000 Kelvin, the carbon line lies below the iron line. Hence we can use coke. Coke is nothing but carbon is used as a reducing agent above this temperature. The following free energy calculation also confirms that reduction is thermodynamically favorable. That means for the decomposition of... Now we are going to see how the coke is using as a reducing agent for FeO to be converted into Fe. So these reactions are not essential, just you learn the last equation is enough. See, that is iron oxide when combined with the carbon. That means no need of learning these and all. So only learn last equation alone. FeO, that is 2 moles of FeO, ferric oxide, combined with the carbon, nothing but coke is using as a reducing reagent. Now FeO changes into Fe and CO. Here too, for the formation of FeO to Fe, it requires minus 130 kilojoule. That is del G means here what means gives free energy change. So del G value is minus 130. Definitely the minus value comes, so it will be a feasible reaction, that is thermodynamically possible, it is a spontaneous reaction. For 2 moles of ferric oxide converted into 2 Fe means minus 130 the value is. For 1 mole of FeO, it need divided by 2, we get a minus 65 kilojoule per mole. So the standard, this maybe comes in 1 mark question. The standard free energy change for the reduction of 1 mole of ferric oxide is minus 65 kilojoule per mole. So once again I recall all the applications. See, first point, for the formation of, for the decomposition of silver oxide and mercuric oxide to silver and mercury, only at moderate temperature will decompose. So there is no need for reducing agent. Then second point, thermodynamically feasibility of a reduction of oxides of one metal by another metal. That means the best reducing agent is aluminium can be used. The third point, the carbon line can cut across the lines of many metal oxides. Hence, it can reduce all those metal oxides at sufficiently high temperature. So, the standard free energy change for the reduction of 1 mole of FeO is minus 65 kilojoule per mole. So, these are the applications. That is totally 3 points it came. So, very important question. Now, we are going to see about the limitations of Ellingham diagram. Now, we are going to see about the limitations of Ellingham diagram. So, observations we saw, then applications also we saw. Now, the only 2 points for the limitations of Ellingham diagram. So, Ellingham diagram is constructed based only on the thermodynamic consideration. So, thermodynamic consideration means how much amount of heat, whether we have to give the supply of heat in a limited amount or excess amount of heat we have to give for the decomposition of metal oxide to metal, or what type of reducing agent we are going to choose. So, these are all called as a thermodynamic consideration. It gives only information about the thermodynamic feasibility of the reaction, but does not tell anything about the rate of the reaction. That means thermodynamic feasibility, whether the reaction is possible or not, how much amount of heat we are going to give for the decomposition of a reaction, we can get the information from the Ellingham diagram. But this diagram does not tell anything about the rate of the reaction. That means how much time it takes to complete the reaction, or within a 1 hour or within a 2 hours. So the rate cannot be predicted by using Ellingham. So it does not tell anything about the rate of the reaction. That means moreover, it does not give any idea about the possibility of other reactions also. That means he only chose manganese oxide, nickel oxide, zinc oxide, copper, aluminium, chromic oxide, etc. So what are the metal oxides given in the graph alone, he explained. He does not give any idea about the possibility of other reactions. That means other metal reactions cannot be taking place. This is the first limitation. Now coming to the second limitation is the interpretation of del G is based on the assumption. That means what is the assumption we are taking here means all the reactants, that the reactants are in the equilibrium with the product. That means we know what do you mean by equilibrium reaction. How much time it takes to complete the formation of the product. The same product can also decompose to give the reactants. Such a reaction, that is decomposition of HI to H2 plus I2. The formed H2 and I2 combine to give HI. This is called as a equilibrium reaction, that is reversible reaction. So here the interpretation of del G is based on the assumption, that is we are taking all the metal oxide reactions after decomposing metal oxide to metal. That metal combined with oxygen to give metal oxide. Now metal oxide decomposed to metal and oxygen. So such reactions, so such assumptions we are going to take here. The interpretation of del G is based on the assumption that the reactants are in the equilibrium with the product, which is not always true. That means we assume that all the metal reduction process fully in the equilibrium condition. So these are the 2 limitations. Once again I recall, Ellingham diagram is constructed based only on the thermodynamic consideration. It gives information about the thermodynamic feasibility but not telling anything about the rate of the reaction. And also it does not give any idea about the possibility of other reactions also. Second point, the interpretation. Interpret means the values of del G. That is del G value, whether it is a positive or negative, which is based on the assumption that the reactants are in the equilibrium with the product, which is not always true. So I think you are very understood the limitations, applications and observations of Ellingham diagram in this video. Thank you.